So today we are going to calculate omega, the density of a state or number of accessible states. State in a statistical system. By statistical, I mean by statistical a system with a large number around 210. So, just before do the calculations, I need to remind you something about the intensive and the extensive parameter, because there is a very interesting physical concept about the change of these two parameters. You know that the intensive parameter, the parameter doesn't change by the size, so T and the other one. T and the energy and this and the other one, like pressure and the chemical potential. That's the one which I want to today to talk about a little bit about the intensive parameter before to go to the calculations. And the extensive one was the one we changed by the size. So as you know, the pressure, volume, entropy, and the number of the particles is the extensive parameter, the number. So there is an observation. The observation is that the delta of the quantity as work is always proportional to the change of the one intensive parameter or intensive variable multiplied to the change in the extensive one. One of them, you actually you're familiar with one of them at least. So you know that del W is P dV.
With minus sign.
Yeah, with minus. What minus? We are talking about not the form which is appear in the first law of thermodynamics generally. But yes, you can write it by minus, definitely. So look at that. This is the energy, change in the energy, and this is the pressure is the intensive parameter, doesn't change, and that's the extensive. And there is another example, dq TdS. Actually, this equation can be used to define the entropy of the system. Anyway, Q is also here the type of the heat, flux, or heat energy. T is our intensive parameter again, and this is the extensive parameter. So these two terms came from the first law of thermodynamics, but there is another equation related to the change in the number of the particle, mu dn, which we can call it that as a definition for the chemical potential. So it could be a d of the some type of the energy also. You can write it like mu dn. Again, this is the extensive parameter and the mu is intensive parameter. But this is not what the concept which I want to focus today on that. The concept is that I want to tell you that if the extensive parameter change, so it should be a change in the energy of the system. And not only that, I want to tell you that if for two regions of the system, or two systems in the contact, the balance between or balance among intensive parameter Greek parameter intensive positive parameter is broken, then you will observe a type of flux. And movement, actually. Sometimes this movement is mechanical movement. I mean, really, the wall, for example, is changing. Look at that. For example, you have a container, and this container has two parts. One pressure is P1 and P2. As long as P1 is equal to P2, so you have a hydrostatic balance. It means that there is no reason to see the movement of this boulder. But when the balance of the pressure is broken, for example, P1 less than the P2, so P2 is greater than the P1, so the wall will be changed. Huh? The wall. Pressure, exactly, pressure, the mechanical force. So you will have the mechanical movement, actually. Moving. Pressure, that's very easy to understand that. And this mechanical moving can be related to the flux, to some kind of hydrodynamic flux. I mean, you don't see that as some particle, but actually, from the physical point of view, it seems that some particles are moving from this part to this part, some hypothetical particle. Some particle doesn't exist. Just to explain the flux. So it will be some flux from here to here in this direction. And that will be very clear if you are looking for the temperature. If you have a container or the room and you make partition to that, to two parts, if T1 is greater than the T2, if T1 is equal to T2, you will have which kind of the equilibrium or balance? You have a thermal balance or thermal equilibrium. Huh? Balance. Balance is a very important concept, especially when you are talking about the chemical reactions or something. In chemistry, it's very important. But if T1 greater than the T2, according to the thermodynamics, you know that it will be some kind of heat flux here. This is exactly what is happening in convection effect in atmosphere, for example, even in the room. When the temperature is hotter, so the level of the temperature is increasing, is going top, while there's some kind of the heat flux. So it should be some heat flux from the left to the side. Heat flux. And the important thing is that, this is very interesting. You have a container, and this container have two parts, partition. And the chemical potential in the first is mu1, and for the next one is mu2. If mu1 is equal to mu2, it should be one such kind of we call it chemical balance. Huh? Chemical balance. Exactly. For example, if you have this simple chemical